What's up guys, this is Waleed and today's problem is activity of phosphorus. So they explain a little bit about it and then let's go to the problem. So P32 has a half-life of 14.28 days, atomic mass of 31.973, and it's a beta decay, emits an electron with energy of 75 kilo electrovolts and RBE of 14. Okay, and we're going to use the fact that the initial activity of that phosphorus is 1.3 mega BQ. Okay, so the first thing we're going to do is we're going to find the decay constant, which is ln2 divided by the half-life, so ln over 2 divided by 14.28 days, and then I'll make it easier and then we'll switch everything to per second. Okay, because if you look back in here, it's per BQ, and BQ is decay per second, so we don't want it to be decay per day, so we're going to switch it to decay per second. So we're going to do that by, let's zoom in, so day divided by 24 hours times hour, 60 minute times minute divided by 60 second. Okay, so for this guy I got 5.61 e to the negative 7. Okay, so then we go to the fact that dN divided by dt is equal to 1.39 mega BQ. It's going to be equal to N times the decay constant. So from that we can find number of N. So N is going to be equal to 1.39 divided mega BQ divided by the lambda, which is 5.61 negative 7. So from this guy I got 2.47 e to the 12. Let me write it down over here. 2.47 e to the 12. That's how many particles we have. Okay. So from there we go to find, so now n, we need to find how much were decayed, so how much after these 6 days passed by. So n naught e to the negative lambda t. Okay, so n is going to be equal to 2.47 e to the 12 particle divided by times e to the power negative 5.61 e negative 7. Line negative 7 times 6 days, and we're going to switch the days to seconds. It's times 24 times 60 times 60. When do we close that guy? So n was equal to 1.846 e to the 12th particle. Okay, so now we're looking at delta n. Delta n is e naught minus n. So n naught was 2.47 e to the 12 minus 0.84 e to the 12. And for this guy I got 0.62 e to the 12. So that was the difference. Okay, so particle have lost. So for this one, 6.2 e to the 12. because for every decay, there is electron that was going out, okay, as an energy. So there was 0.62 e to the 12 particles have been decayed, okay. So what is the total amount of energy absorbed by the patient body during this period? So we have 0.62 e to the 12 electron during this period, so times 705 e to the third, okay, because they told us that with every electron there is 705 kilo electron volt. Cool. The E3 comes from the kilo electrovolt. So from this guy I got 4.371 e to the 17 electrovolt. Cool. So for this guy, the last one, the radiation absorbed by 128 grams of tissue. What is the patient equivalent absorbed dosage? For this guy, we divide the energy we got, 37 e to the 17. This is an electrovolt, so we change it. This is an electrovolt, so we change it to a joule. So 1.6 times 10 to the negative 19 joule. We divide that by 0.128 kilograms. Okay, so for this one I got 0.5685. Okay, and then what we're gonna do is let me write it down over here. 685, this is meter squared per second squared, and we need to change it to radian, so multiply by 100 rad divided by meter squared divided by s squared. Okay, so for this one we got 56.85 rad. Okay, and then we just multiply it by how much is the RBE. So mine was 14, so multiply it by 14, which is going to be equal to 764.5 REM. Okay, so that's the answer for this, 764 REM. Alright guys, hope this helped. Let me know if you have any question. Take care, bye.